Okay, so we are still in chapter 7. We are looking at connections and beam shear. This is example 2 in our examples. So we have a wooden beam that's fabricated by nailing 3 pieces of dimension lumber as shown. The cross-sectional dimensions of the beam are shown. The beam must support an internal shear force of 750 pounds. Determine the maximum horizontal shear stress in the cross section for V equals 750 pounds. If each nail can provide 100 pounds of horizontal resistance, determine the maximum spacing S for the nails. If the 3 boards were constructed by glue instead of nails, what minimum shear strength would be necessary for the glued joints? Okay, so we have a wooden beam. We want to find the maximum horizontal shear stress. So we know that normally occurs, depending on the cross section, at the centroid. And our equation is VQ over IT. If each nail can provide 100 pounds of horizontal resistance, so that's that shear, that transverse shear that's going up and down the beam, determine the maximum spacing S. So spacing is the length apart down the beam. And we know that it's our shear flow is VQ over I, and that our shear flow for fasteners like this is going to be the force of the fastener, divided by the spacing. And then we can go back and find the shear strength. So we can go back and find the shear stress that occurs from that shear flow and determine the strength of glue that we need. So for all of these things, we are given V, we are given I, and we'll have to find Q. So normally, our maximum shear occurs at the centroid, and that equation is VQ over IT. My V is given as 750 pounds. My I is given as 230.933 inches to the fourth, which is perfect. Now we need to do thickness. So when we are looking at the maximum, it usually occurs right here at the centroid. We need that thickness. So I have 2 times 2 inches. So my thickness is 4 inches. Okay. Now I can either use this area above, in which case I would have 2 rectangles plus another rectangle, or I can just keep it simple and we're going to use this area below. So y to the bottom is 4.6 inches. And I know that the centroid of a rectangle is right in the middle. So this is going to be 4.6 inches divided by 2 for that moment arm. So when I'm looking at this Q value, I'm going to have 2 because I have 2 areas. My area is base times height. And then my moment arm is going to be that 4.6 divided by 2. Okay, so we now have all of our values. So our maximum shear stress equals 750 pounds. Our Q is going to be 2 times 4.6, that's our area, times 4.6 over 2, that's our moment arm, divided by 230.933 inches to the fourth, and then we have 2 times 2 inches for our thickness, and when I multiply all of this out, I get 34.36, and I'm in pounds, so PSI. Okay, now we need to determine our spacing. So, we have this equation that the force of the fasteners divided by, I don't know why I keep putting an S there, the force of our fasteners divided by the spacing equals VQ over I. This is our shear flow that the fasteners must resist. Again, V is given, I is given, the force of our fasteners is given, and we need to find this value of what is our spacing. Now keep in mind, spacing is that length, again, down the beam. How many inches on center do we need to put these fasteners in? So we are attaching, let's find a different color here, we are attaching this member with the nails. Okay, so this is going to be my Q that I'm looking for in terms of fasteners. So what is Q? It is area. Well, that's pretty easy. 4 times height times 2, okay, that's my area, times the centroid. Well, I'm told that y to the top is 3.4 inches, so we can go all the way to the top, 3.4 inches, okay? And I know that this top piece is 2 inches tall, which means coming back down to the centroid is 1 inch. So if that's the case, this moment arm here has to be 3.4 minus 1. 3.4 minus 1. So we're going to rewrite this in terms of S. S equals cross multiply the force of the fasteners times the moment of inertia divided by VQ. So our spacing equals the force of the fastener. We have 2 and they're 100 pounds each. See, 1, 2. My moment of inertia is 230.933 inches to the fourth divided by 750 pounds. So our pounds are going away. And then Q. And Q was area, 4 times 2, times 3.4 all the way to the top, minus 1 inch back down. So we have 2.4 inches. So everything's in inches and pounds. And I get a spacing of 3.21 inches. Now this is the maximum spacing. I could not go up to 3.5 inches. This is the maximum it can be. So most likely I would say I need them 3 inches on center. That way we have a little bit of wiggle room, but we're definitely less than the max. Now we're going to look at the strength of the glue. And when we look at this, our shear flow that we have to resist is this VQ over I. And when I'm looking at that shear stress, we've already figured out this value. We've already figured out the V for this, the I for this, and the Q. We have the Q. And so now we need to look at the thickness. And we have a glue strip here and a glue strip here. Do you see that glue? We'd have to have glue in there and glue in there. And so we're looking at a very thin piece, and clearly the glue would go all the way back down the length, but we have, this is where we're going to have that connection. So if I put glue in here instead, I would glue there and glue there. And when I look at that, I have 2 times this thickness, 2 inches. 2 inches and 2 inches. So we can go back and our shear stress equals, okay, V, 750 pounds, Q, 4 times 2 times 2.4, okay, over I, 230.933 inches to the fourth. So that is our shear flow Q. And then we have 2 times 2, we have 4 inches. And when I calculate that out, I need to have a strength of 15.59 psi as the minimum strength of the capacity of the glue. Okay, so we didn't really talk about this, but we're going to go ahead and we're going to figure out how do we sketch this shear stress distribution. And I know that it's parabolic with the maximum here. And so when I look at this, I have a transition here in thicknesses, and I'm going to end up with then kind of a bump. And if I think about what does the shear stress distribution look like, it is 0 at tops and bottoms. 0, because we don't have any area beyond. And I'm going to have a maximum here of 34.36. When I'm coming down, it is consistent in thicknesses, okay? When I am coming down from the top, I have 2 thicknesses. So when I have VQ over IT, VQ over I is the same, but I'm going to have a thickness of 1, 2, 4 inches, and I'm going to have a thickness of 8 inches. And that's why we end up with this kind of a bump right here and right here. So I already know this value is 34.36. Let's figure out these. Okay, let's figure out those. So we're going to draw, I'm just going to draw a cross section that is just this top part. And we're going to ignore the fasteners right now because we're just kind of coming down. And I'm going to move this over. D, our made up D. And I know this distance is 3.4 inches. And this is 2 inches thick. So it has to be 1 inch to get up to this point where we have this transition. So when I'm looking at Q here, let's find, I guess, a different color maybe. Orange. Okay. Then I am looking at, this is my Q, because I'm looking at the shearing of the wood right here. I'm not looking at the failure of the fasteners. So when I'm looking at this Q, I can see it is 8 inches, 4, 5, 6, 7, 8. It is 2 inches tall. And then the centroid is going to be, it's the same centroid we had up here. It's going to be the centroid of that 2 inches back down. So 3.4 up minus 1 inch back down. So this centroid is 2.4 inches tall. So when I want to find the shear stress at my transition, then I'm going to have VQ over IT. So I'm going to have 750 pounds. Okay. My Q is going to be base times height times moment arm divided by I, 230.933. And then I have this little thickness. Okay. When my thickness equals 1, 2, 3, 4, 2 times 2 inches, which is 4 inches, then I'm going to get a value of shear stress. When my thickness equals all the way across 8 inches, then I'm going to get a different shear stress. And so when I fill those numbers out, okay, when I'm dividing by 4 inches, okay, let's just go through here and look what we have. So I have 750 times 8 times 2 times 2.4 divided by 230.933 divided by 4 inches. And I get 31.177. And that's where we're going from the much, much thicker 8 inches. So we're going 8 inches, 8 inches, 8 inches, 8 inches. Oh, now we're at a thickness of 4 inches. So that's going to be 31.18. And remember, we already said the maximum was 34.36. And now let's do 8 inches. So we have 750 enter, 8 times 2 times 2.4 times 230.933 divided by 8 divided by, and I get 15.59 psi. And so that's going to be this value here, 15.59, because I'm coming down with 8 inches of thickness, 8 inches of thickness, 8 inches of thickness. We're down to 4 inches of thickness. And then we continue. So that would be how we would sketch that number out.